in figure 9.5, we have three different figures here, and let's sort of walk through the top one and then we'll compare the next two. So this velocity distribution, you can see, is inviscid, right? It's uniform. There's no change in the velocity here. So that is the classic inviscid velocity profile. And it's coming in at some velocity u. Now it encounters a flat plate oriented into the flow here. And this flat plate, even though it's shown with thickness here, is considered infinitely thin. And you might ask yourself, why do we need to consider it infinitely thin? Well, if it had thickness, then there would be a point here where we would have the velocity impinging on a surface that was perpendicular to it. And we'd essentially have a pressure force here that would be different than the pressure force down here, and we would have pressure drag on the flat plate. But if it's infinitely thin, really all we have is viscous drag. And so by employing an infinitely thin flat plate, what we're doing is trying to separate the effects of pressure from the effects of viscosity. So we have some length that starts at 0, the coordinates are 0 here, and move in the x direction, and the plate has length L. The velocity out here is u, right? And as we remember, the no-slip condition says that the velocity actually has to be 0 at this plate. If the plate's not moving, then the velocity has to be 0 here, and we know that it has to become u out here, and so in between here, it's somewhere in between. And we also remember from our discussion of momentum in Chapter 5 that the only thing that changes the momentum of a flow is a force. And you can see here that we have a viscous force acting on the flow to change the pressure or the velocity profile from an inviscid velocity profile to a clearly viscid velocity profile. The reason that we are trying to differentiate, we're trying to draw a line around this and say that outside here, the viscous effects are not important. Inside here, the viscous effects are important. But let's think about a much simpler case. If we were to assume that all of the flow was inviscid, then we would have no drag on the flat plate, and thus this wouldn't be a very useful calculation. You can imagine that if the flat plate were fairly small, the shear stress is fairly small, the area is fairly small, then the viscous force is fairly small. However, even if the viscous shear stress is small, if the area is large, then the viscous force becomes increasingly large. And so at some point, this is just a bad assumption. And so that's what we're getting towards is trying to identify the place where the viscous effects are important and the viscous effects unimportant. If we can draw a streamline out here in the inviscid region, then we simply use Bernoulli's equation to relate the velocity or pressure at these 2 points, and it becomes much simpler. So we're trying to identify the region where the analysis is fairly simple from where it might be a bit more complex. And so we need to come up with some length. We need to come up with some height at some distance from the leading edge here, at which below which the viscous effects need to be considered, and above which we can ignore them reasonably. Okay, and we'll get to that here in a second. As you can see, we've got Reynolds number is equal to 0.1 here. If we scoot down to the next one, we've got Reynolds number is equal to 10. And so if you think about what Reynolds number is, of course, it is the velocity times the characteristic length divided by the kinematic viscosity. And if the kinematic viscosity and the characteristic length don't change, then essentially all we've done is increase the velocity here. And if we increase the velocity here, we see that this region around the plate gets skinnier, right? It doesn't stick up quite so far. It gets a little smaller, right? But also I want to point out what happens to the velocity profile, right? We have a nice sort of lazy swooping motion here. As this boundary layer is compressed, as this region is smooshed down, right, that velocity profile gets a bit steeper. And as we increase the velocity even further here to 10 million, we see that this still needs to go from 0 to u, but it does it in a much smaller vertical distance, which makes du dy much, much larger. Right? The streamwise velocity change per increment of vertical space change gets much, much larger. And you can imagine that even from what you know of viscosity at this point, that the shear stress must increase significantly. So that's the gist here. The idea is, of course, we've got the inviscid velocity profile, we've got the viscid velocity profile, and we're trying to find some means of differentiating between the inviscid region and the viscid region. Now, as you'll see over here, we look at the bold terms, we've got this region called the boundary layer. And the boundary layer is essentially this shaded part right here. And we typically only worry about this above the plate. And so we'll see lots of stuff looking like that here fairly shortly. But this boundary layer thickness is given by the variable delta, right? This is a lowercase Greek letter delta. So you can see at every L, we can find a delta, okay? So, why does that matter? Well, what we really want to be able to do is figure out what the velocity profile is here. And if we figured out what the velocity profile is, then we could figure out what the wall shear stress is. We could multiply that by the absolute viscosity and get the, we could, the shear strain rate, right? The velocity profile gives us du dy. We multiply that by the absolute viscosity, and that gives us the wall shear stress. We take the wall shear stress, multiply it by the area, and that gives us the viscous force. And that's what we're really after. So we look at figure 9.6 here, and again we have 3 frames. We'll go through them bit by bit. So in this case, we have these streamlines here over a cylinder where the Reynolds number is fairly small. If we increase the Reynolds number, we begin to develop this boundary layer region here, right? And outside, we can say that the viscous effects are unimportant. Inside, we are concerned about the viscous effects. And as you saw in Lab 1 and maybe other situations in your life, maybe standing by a river and looking at the flow around a rock, if the flow is going this way, and you see this area of recirculation behind. And there comes a point where the flow is flowing over the cylinder and then breaks off, right? And so past this point, in an angular sense, we have this circulation bubble. And if we keep increasing the Reynolds number up to 100,000 here, we get a smaller region where the viscous effects are important, and we get some much more turbulent flow here in the separated region, and we might get a change in where this boundary layer separates. So we're going to start talking about the boundary layer characteristics in an effort, again, to be able to calculate the viscous force on a flat plate. This is actually a video that you can watch that's posted on the Blackboard site, but essentially you can see the velocity profile is the light region here over this flat plate. And we're going to talk about this, but it might be useful to you to actually watch a movie of that. So let's spend some time talking about what's going on in figure 9.7. So first we'll focus on this top line here. And what we have here, again, is the inviscid velocity profile, right? There's no change in the velocity as a function of height. So du dy is 0, right? So there is no shear stress. And these boxes represent just basically a 2D chunk of fluid. And as this fluid traverses, so each of these are snapshots in time. So as this fluid traverses from left to right, we see that there is no change in the shape of the box. There's no distortion, which means that there is no viscosity acting on that chunk of fluid. And we compare that down here. Also notice that the velocity profile, the width here, is the same at each point, right? Notice down here for this one, it's the same here in the inviscid region, but now it passes through the boundary layer into the viscous region. And we have some deformation, right? And anytime we have a change in the velocity profile, we know that there must be a force at work. That force in this case is viscosity. We also have this velocity profile that develops because the flow must be 0 here at the flat plate, and it must be u out here in the inviscid region. And we've marked this as being delta here, which is the height of the boundary layer. And we can see that as L increases, we get more and more deformation. And at some point, the boundary layer goes from this nice smooth curve and it hops up and basically makes this other smooth curve. In this region right here, we have the laminar boundary layer. And when we see this hop, we can use that to identify the beginning of the turbulent boundary layer. Now we have sort of gentle deformation here, but as soon as we get into the turbulent region, as we've seen previously, we have a great deal of mixing that is characteristic of turbulence. So we come down here and we start to think about how to describe this. And you can see that we're using the Reynolds number. In previous cases, the Reynolds number we've defined as the characteristic length has been, say, when we were doing modeling in similitude, maybe the length of a car or the chord on an airfoil or something like that. In pipe flow, the characteristic length was the diameter. But in this case, there's not a real obvious choice here, right? Because this plate has no thickness. We'd like to be able to describe the length of this plate generally. We could, I guess, use the length of the plate, but overall length of the plate. But what if we have different length plates? There doesn't seem a real obvious choice for the Reynolds number characteristic length, except thinking about the distance from the leading edge here, right? So if we say that this is x is equal to 0, and then we increase x as we move away from that point, we can define the Reynolds number by the distance from the leading edge, which we'll call x. And so the Reynolds number in this case is defined by that distance from the leading edge. And as you might guess, if L is increasing as we move in the x direction, if x is increasing in the direction from left to right, we're increasing in Reynolds number the whole time. And so at some point, this Reynolds number becomes high enough that we trip from laminar flow to turbulent flow, right? So no matter how smooth the inflow, no matter how slow, at some point, given a long enough distance, the flow will always trip to turbulence. And as you recall from pipe flow, for Reynolds numbers based on diameter less than 2100, we can consider the flow laminar. For pipe flow, Reynolds number based on diameter greater than 4000, we can consider it turbulent flow, and somewhere in between is the transition region. We have a different range here. So below about 200,000, we typically consider the flow laminar, and above 3 million, we consider it turbulent. The number that is typically given in the book and is given a few pages from now, but you should write down, is the critical Reynolds number. The critical Reynolds number that identifies the marker, the boundary between laminar flow and turbulent flow, is 5 times 10 to the 5th. And that is based on the distance from the leading edge here. Okay?